Okay, it's Brian, and we're going to look at two concepts related to energy today, and those are the concepts of work and power. Now let's start by thinking about work. We've talked about this basic energy model, and we use this red line here to separate basically the system from the rest of the universe. But we know that there's no totally isolated system. And in fact, there are ways to get energy in and out of systems, and one of them is work. I can put work in, and I can take work out. That's one thing we can do. The other thing we can do is heat. I can put heat in, and I can take heat out. Now we're going to talk about that when we get to talking about thermodynamics, which is really the stuff of chapter 12. But today we're going to talk about this idea of work. And work showed up in our basic equation. Okay, we have the initial kinetic and potential energies of our system, and then we had a term here for work, and that is an energy input to the system, or if it was a negative number, it could be an energy output. Okay, and we're going to come back to talking about heat transfers. That's something we'll take a look at later. So work we already have talked about implicitly, and typically we've set work equal to 0 because we said we're dealing with an isolated system where there isn't any work coming in or any work going out. But now we're going to start thinking about systems where that's not true. And to be able to put energy into a system, i.e. to do work, you apply a force through a distance. Basically, you push on something. And pushing on things is how you do work on them. And yeah, the only force that matters is the force that's parallel to the motion. That's kind of a technical point. This is the relationship that will be the crucial one for us. That the work is equal to the force times the distance. Now let's take a look at a problem here that deals with work. So here's the question. Why is it easier to raise a large load by pushing it up a ramp rather than lifting it directly? Does the person use less energy to complete the task when they push the box up the ramp? That clearly is an energy problem that we can solve. And let's go ahead and take a look at a detailed view of this. So we take a 5 kilogram box and we raise it by 1 meter, and we do two different things. One, we raise it directly. Two, we push it up a 30-degree ramp. Two questions. What is, one, the necessary force necessary to raise the box? Two, what is the work done in each case? We are implicitly saying, like basically the box is the system. And if I'm raising the box, I am putting work in. Work is going into the system. And so I, as an external agent, am applying a force through a distance, and so I'm putting in an amount of work that's just equal to the product of the force times the distance. And of course, we know what's going to happen. I'm going to increase the potential energy of the box. So if we use our basic relationship, it looks like this. Initial kinetic plus the initial potential plus work is equal to the final kinetic plus the final potential plus the change in thermal energy. Well, change in thermal energy would be if there was friction. Let's assume it's a frictionless ramp because, oh, we're told that. Frictionless ramp, score! Let's assume the box starts at rest, finishes at rest. It starts on the ground, so let's take that as a 0 potential energy. And my equation is saying the work that I put in is equal to my final potential energy. And that makes sense. I'm just putting in work, and the work that I'm putting in, I'm increasing the energy of the system, specifically the potential energy of the system. But let's go ahead and calculate these two cases, okay? And we're going to first calculate forces, okay? So that's the first piece we're going to do is look at forces. And then second, we're going to come back and take a look at work, okay? Now, first off, if I raise the box directly, it's a 5 kilogram box. And if I take that box and I raise it directly, okay, the free body diagram for it looks like this. I'm applying some sort of an upward force. And I'm just going to call it F. I don't care. I could raise it with a cable, in which case it'd be a tension. I could raise it directly by pushing with my hand, in which case it'd be a normal force. It's just going to be a force F. And if I'm raising it at a constant speed, that force F is just going to be equal to the weight force, because if I'm raising it at a constant speed, okay, the velocity vectors are staying constant. That means the net force is equal to 0. But the force we're interested in is the force that we're applying. We're applying a force F. That is the force necessary to raise the box. So for our first question, if we're looking for the necessary force to move the box, if we're raising it directly, the force is F, which is equal to W, which is equal to m times g, and if it's a 5 kilogram box, that is 49 newtons. Okay, so that's the amount of force to raise it directly. But suppose we push it up a 30-degree ramp. Okay, so then my situation looks like this. And if I have my box on my ramp like so, and I look at the forces that act on it, okay, so there's a downward weight force. There's an upward force that we're pushing the box up the ramp, and there's also a normal force which looks like this. Now let me go ahead and rewrite that over here so that the vector nature is more clear. So I have a weight force which is going straight down. I have a force which is going up the ramp, and I have a normal force which is perpendicular to the ramp, like so. Okay, that's my situation. Well, as we do in these cases, we're going to take an x-axis that points along the ramp. So that's my x-axis. And if this angle right here is a 30-degree angle, and we're told that it is, okay, we're told that it is, then this angle up here is a 60-degree angle. And so this angle right here is going to be 60 degrees. And I can take that weight force and take a component of it that points along the ramp. Okay, and that component along the ramp is just going to be equal to W times the cosine of 60 degrees, which in fact is 1/2 W. Okay, so that's the force that I have to push with. Because think about this. I've got that force up the ramp, force F. My force down the ramp is just a component of the weight. That's just W times the cosine of 60. Those are the only forces along the ramp. The normal force is perpendicular. And so I can clearly say the force that I'm pushing up the ramp with is just equal to 1/2 times the weight force. So it's equal to 24.5 newtons. It's basically 1/2 of the weight force. So if we compare that to the previous case, the amount of force that we had to apply was 1/2 what it was previously. But now let's think about the second piece of the puzzle, which was the work which was done in each case. Pushing the box up the ramp absolutely requires less force. It only requires half as much force. So think about this. I'm taking the box and I'm raising it directly. Okay, I'm raising it directly. When I do that, the force necessary to raise the box is just equal to W, which is equal to 49 newtons. If I take the box and I push it up the ramp, okay, the force that I have to push with is equal to W over 2. That's equal to 24.5 newtons. Okay, so I'm having to push with less force. But now let's think about the work that's done. And remember, work is equal to force times distance. Well, in the case here where I'm raising the box directly, it starts down here, ends up here. The amount that I've raised it by is just 1.0 meters. That's what we're told. So the work necessary to raise the box is the force we apply times the distance. That's just equal to 49 joules. Okay? That's the amount of work that we have to do. Now let's look at the second case. If we're pushing it up the ramp, and if the ramp looks like this, okay, and the height of the ramp is 1 meter because I'm raising the box by 1 meter. This is a 30-degree angle. Okay, if that's a 30-degree angle, this length, the length along the ramp, is 2.0 meters. So the work that I have to do is a force of 24.5 newtons. That's the force I have to push up the ramp with, times the length of the ramp of 2.0 meters. And so I end up with a work that I have to do of 49 joules. Okay? And so I have to do exactly the same amount of work to move the box up the ramp. And that makes sense because we have conservation of energy. The box begins at a certain height. It goes up by 1 meter. And however I get it there, I've increased its potential energy by 49 joules. How much work do I have to put in? 49 joules no matter what I do, okay? So it can take less force, and in fact it does, but it can't take less work to get the box up the ramp. So that's an example of using work to kind of like calculate an answer to a problem. But more interesting for us is the concept of power. And power is a rate of energy transformation. So if I'm putting energy into a system, if I'm transforming energy in a system, the amount of energy I transfer in a time interval delta t, that's the rate of transforming energy. That is the power. Or if I'm transferring energy, I'm putting in a certain amount of work in a time delta t. The power is the rate at which I'm transferring energy, and the unit is a joule per second, which is a watt. And here's a useful equation. If I am doing work and I'm pushing something at a constant speed v, the power that I'm doing is equal to the force I'm applying times the velocity v. Okay, so those are some relationships for power. Now power, as I say, it is a rate. It is a rate. So if I have this Volkswagen Beetle and I have this Formula One racer and they're both getting up to 60 miles per hour, they both have the same kinetic energy when they get there. But the Formula One racer is going to do it in a lot less time. And so that means that the power, which is equal to the change in energy, in this case the kinetic energy divided by the time, is going to be greater. So greater power, even though you have the final result, same amount of change in energy, but it happens in a shorter time. Let's do some calculations because I'm very, very interested in energy in biological systems, and I want to look at the rate of transforming energy in biological systems. So here's my question. A 70 kilogram human sprinter can accelerate from rest to 10 meters per second in 3.0 seconds. Question, what is the specific power, i.e. the power output divided by the mass in kilograms? And we're doing animals so that we can compare apples to apples. We're going to look at specific power. I mean, clearly an elephant can produce more power output than a mouse. But how about pound for pound? That's what we want to consider when we consider specific power. So let's take a look at this problem. And first, I'm going to strategize. And in strategizing, I'm saying I'm just going to treat this as an energy transformation problem. Energy is being transformed from one form to another. And so I'm going to compute a power as equal to the energy that is transformed divided by the time interval. Now, next up, let's prepare, and let's do a before and after visual overview. So here's what the before and after visual overview looks like. Okay, for my before, I have a runner at rest. And my after, I have a runner moving at speed. So I have a runner kind of like moving along here and moving at a certain speed v. Okay, that's my after picture. And then the question asks what energy changes. And this is a form of energy we haven't talked about. But if we look at our basic relationship, which was the initial kinetic energy plus the initial potential energy plus the work, is equal to the final kinetic energy plus the final kinetic energy plus the final potential plus the change in thermal energy. But let's look at the initial case. No one's doing any work when you're sprinting. No one's pushing you. Your potential energy is zero because you're on the ground. And your kinetic energy is zero because you're at rest. So we have to have something else that appears here. And in fact, the extra piece we're going to add is just chemical energy. And chemical energy in your muscles, okay, is being transformed into the kinetic energy of your forward motion. So the energy transformation that is taking place is chemical energy is being converted to kinetic energy. So we're going to compute power is this way. Power is equal to the rate of change of energy, the rate at which energy is being transformed. The energy that changes is just the kinetic energy. So it's the change in the kinetic energy divided by the time interval. Well, the kinetic energy starts out at zero, and so it's just going to be equal to the final kinetic energy divided by the time interval. That is what we're going to compute for the power. And if we do that as our solve step, okay, the power is just equal to the final kinetic energy divided by the time interval. Okay, that's equal to 1/2 times the mass times the speed squared. And the runner accelerates to 10 meters per second. So it's 10 meters per second squared. And we divide that by the time interval. And the time interval is just 3.0 seconds. But I wasn't looking for the power. I'm looking for the specific power, the power output divided by the mass in kilograms. And so you see cleverly, I've just left the mass as m in this equation. So if I do specific power, the specific power is equal to the power divided by the mass, which is equal to 1/2 times m times 10 meters per second squared divided by 3 seconds, but then I divide that also by the mass, And so I have a mass on the top, I have a mass on the bottom, the mass cancels, and I end up with a value for the power per kilogram of 17 watts per kilogram. And here's my assessment. 17 watts per kilogram, is that a lot? Well, it's an elite sprinter, and we're going to use this number to kind of like judge other things by. Okay, you are going to do a couple of examples in the lab where you're going to measure your specific power, and as you're doing that, I want you to compare versus this number. This is what elite athletes are capable of, okay? And you should be able to do about half that if you're seriously working it. So that's the kind of question we're going to do. And then when we look at other animals, we're going to compare them back to the power of the human sprinter. Now, I also want to talk about this. Remember back when I was talking about forces necessary to make cars go down the road. Okay, to make a car go down the road, it takes about 180 newtons to make my car go down the road at about 20 meters per second. And as the car is moving down the road, the question is what energy transformation is taking place? Well, if it's going down the road at a constant speed on level ground, our basic relationship looks like this. We now have chemical energy on the right, and chemical energy plus the initial kinetic energy plus the final initial potential energy plus the work is equal to the final kinetic energy plus the final potential energy plus the change in thermal. When your car is going down the road at a constant speed, since the speed is constant, Ki and Kf are equal, so I can cancel them. No one is pushing you, so there's no work that's being done. If you're on level ground, the potential energy is not changing. And so basically what's happening is this. Your car is turning chemical energy in the fuel into thermal energy. That is all that you are doing. You are just warming up the air as you're slamming into it. You're kind of like speeding up the air molecules and making them move faster. That's the energy transformation that takes place. Now remember back when we were talking about the force necessary to make a car go down the road. It takes about 180 Newton force to make my car go down the road. But Milo can pull with 180 Newton force. That is easy for him. So how come I don't just hitch Milo to the front bumper of my Scion XB and have him pull me down the road? And let's take a look at how much power it would take for him to pull the car at that speed. And let's do a strategize. In this case, we're going to be looking at the power is equal to the work done divided by the time interval. Okay, we're going to look at that. So if we're looking at doing an external input of energy. And for a preparation, we're just going to say this. We remembered that in such cases, we could say the power was just equal to the force times the velocity. So the car is moving down the road at a constant speed. And to keep it moving down the road at a constant speed, I have to apply a force of 180 newtons. And the power necessary to do that is just going to be the product of the force that I'm applying times the speed that I'm moving at. And if you do that calculation, power is just equal to the force times the velocity. I end up with a power of 3,600 watts. 3,600 watts, or 3.6 kilowatts. And here's my assessment. Could Milo do this? And the answer is no, he sadly cannot. 3,600 watts is way more than an animal is capable of. And we know that this is true because if I could do it, doggone it, I would do it. Milo would have a blast and we would be the talk of the town. But Milo can't pull with this much power. Like, he's just simply not capable. He's probably also not capable of running at 20 meters per second, but let's leave that aside. That power output is just way too much for animals to be able to do. And let's take a look at some typical numbers. So for Milo, I figure his mass is about 25 kilograms. He can pull with a 200 Newton force, and his maximum power output is about 750 watts. That's what I estimate. That's about 1 horsepower. So 1 Milo power is about 1 horsepower for a burst of power, but a sustained power is only about 200 watts. So in fact, to be able to pull my car down the road, I would need about a whole bunch of Milos, which would be kind of awesome, but also somewhat impractical. Now we're getting into talking about your body using energy. And when we start talking about your body using energy, we have to deal with questions to make that efficiency. And we're going to talk about the basic idea of efficiency next and start talking about the efficiency of your body in performing certain tasks. We'll talk about that next.